Hello, Chem1A. This is Chapter 7, Lecture Video 9, our last lecture video on gases, and at least in Chapter 7. And we're going to be talking about when the ideal gas law really doesn't work, right? We always assume that gases are behaving ideally when we're using the ideal gas law. Well, what if they aren't behaving as ideal gases? And so let's look at that, all right? First, we need to understand those assumptions that we are assuming when we assume that a gas is behaving ideally. And one of them is that they have no volume. And the other one, and more important in this regard, because most of the time we can pretty much always assume they have no volume, even though it's not true. It's close enough because their volume is so small compared to the container that they're in. But the second assumption is that they do not attract or repel each other. And this one is less, there are definitely examples of when that is not going to be a true statement. So let's talk a little bit about an analogy. So I'm going to draw a little bit of a picture to kind of help us understand when gases are not going to attract or repel each other most. Okay, so aside from my drawing being, as good as I got, I'm not the best artist. Hopefully you can kind of understand what's going on here. So let's talk through this. So think about these two scenarios. Let's talk about when the conditions that we're going to talk about when we're talking about whether a gas is behaving ideally or not is really pressure and temperature. So in a scenario, let's say the two people in these cars, right? They're friends. And the two people in these cars are also friends. One of my biggest pet peeves when I'm in a parking lot and in a car, one of those things gets me really close to being like a road rage person. I'm generally not. I don't get that upset. But one of the things that could is, it's happened to me before. I'm behind this car, right? I'm sitting here in this car here, and these two people in these cars are passing each other in a parking lot, and they're friends. So they get up close to each other and they stop to talk to each other while I'm sitting behind this person trying to go. It's one of the biggest pet peeves I've had to experience, and it's so annoying and so inconsiderate, right? Like, you're talking to each other, I'm waiting for you to just move, right? But in that scenario, let's say these two, they drive forward until they get to each other, and now we're sitting here and these two cars are pulled up alongside each other, and the two people are talking to each other and stopped in the parking lot, right? Why did that happen? Would that happen in the same scenario if the two cars were passing each other on the freeway and they ended up being friends? Absolutely not, right? These two guys are going to zip past each other without ever even noticing that they were there, most likely. What's different about these two scenarios? Well, the rate of velocity that the cars are going, right? On the freeway, these cars are booking it probably, in California at least, probably going 80 miles per hour, right? Whereas in the parking lot, they're probably going like 10 to 15 miles an hour. Well, it was much more likely for the two friends to notice each other and then stop and talk to each other in the parking lot if they're only going about 10 to 15 miles an hour, because they will be able to see and notice each other. This is kind of like an attraction, right? So in this scenario, the faster the gas particle or the cars are going, the more likely there is no attraction or repulsion, right? Because if they're going super fast, they're going to zip past each other without even noticing that they did pass each other, the two gas particles, or in this case, the two friends in cars. Regardless, the two particles are not going to repel or attract each other because of the fact that they didn't even notice they were near each other because they were zipping past one another. Well, what makes gas particles move fast? Well, temperature does, right? So one of the things that we want for a gas to behave ideally is high temp. And that's really what my little picture here is supposed to display, right? The slower you're moving, the more likely those two gas particles, when passing each other, might attract or repel each other. Okay, so the other aspect that might play a role in whether a gas might attract or repel each other has to do with distance, right? So speed is really great. That's the high temperature bit. The faster you're moving, the less likely a gas is to attract or repel, or in other words, the more ideal that gas will behave. However, what if we're moving past each other and we're really far away from each other, right? These two people. If these two are walking opposite each other, and they are, but they're really far away, right? Are they likely to stop and say hello to one another? Let's say they're friends again. They might not notice they walked past each other because they're so far away. Versus these two people walking past each other, if they're friends, are gonna probably stop and say hi to each other, right? The same is true for gas particles. The closer our gas particles are together, the more likely they're going to be to attract and repel each other, right? Um, the farther apart they are from each other on average, the less likely they're going to attract or repel each other. So the second condition, right? Our first condition was our high temp. Our second condition is going to be a gas is going to behave most ideally when they're really spread apart. Well, what controls that? Pressure does. The higher your pressure, the more condensed our sample is of gas particles, the closer they are together. So at low pressure, the gas particles are really far apart from each other on average, so they're less likely to interact with one another at all. Attraction, repulsion is all less likely to happen, which means they're going to behave more ideally. So, just to kind of reiterate, right, gases are going to behave very ideal when we're at lower pressures and higher temperatures. The higher your temperature, the lower your pressure, the more our gas will behave ideally. The opposite is true as well, right? So if our gases are under high pressure and low temperature, those gases are going to start deviating from ideal behavior because primarily they're going to start attracting and repelling each other. This will cause issues if you're trying to use the ideal gas law to predict their behavior under these conditions. So let's talk about that. What if our gas is not behaving ideally? Well, then we can't use the ideal gas law to calculate anything about it. So if in the problem you're told, hey, this gas behaves like a real gas, is not behaving ideally, well, we have another equation for that. It's known as the van der Waals equation, and you can see it right here. Now, why don't we just always use this equation? Well, as you can see, it's a much more complex equation than the ideal gas law. This is a lot more complex than PV is equal to nRT. So if the ideal gas law works pretty much good enough, then we're probably going to try to use that as opposed to this van der Waals equation. But the van der Waals equation, it basically takes those issues that we're having with our ideal gas assumptions and corrects for them. And so that's what the A and the B are in this equation. They are constants. And they're constants that correct for the assumptions we're making about ideal behavior. One, that attractions and gas, in real gases, there are attractions and repulsions between the gas particles. And for B, it corrects for the fact that, hey, guess what? Real gases do occupy volume. Their particles do. Now, it's not a large volume, but it is there. Now, A and B are constants. They change depending on the identity of the gas. All right, and they're different values from each other as well. So if we're talking about CO2, it will have an A and B value that is specific to it. And if we're talking about H2O gas or hydrogen gas, they'll all have different values for A and B. So let's do a problem with our equation. What is the pressure of a 34.6 liter container with 30.6 moles of hydrogen at 14.5 degrees Celsius? The van der Waals constants for hydrogen are this and this. So in this equation, pretty much I'm going to give you everything except one of the unknown variables, and you're going to need to solve for it, right? So in our equation, we have, if you remember from the previous slide, pressure plus N over V, A times N over V squared, plus, or sorry, not plus, times V minus Bn is equal to nRT. Okay, so if we're looking at this equation, we have A, we have B, we have V, we have N, we have T in the wrong units. It needs to be in Kelvin, just like the ideal gas law. And so we can plug in pretty much everything except for T. Once we change it, we'll be able to, and solve for pressure. So T we know is 14.5 degrees Celsius. We got to change that to Kelvin, so we got to add 273.15. This will give us 287.65 Kelvin. All right, so now we're pretty much ready. We have pressure plus 0.244 ATMs times liters squared over moles squared, and that's times 30.6 moles over 34.6 liters squared. And that whole thing is going to be times our volume, 34.6 liters, minus 0.0266 liters over moles times our moles, which is 30.6 moles. All that is equal to 30.6 moles times R, which is 0.08206, and this is atmospheres, liters, that whole deal. I'm going to leave out the units, times 287.65 Kelvin. All right, and we'll clean that up as we go down the slide. All right, so let's do some condensing of values, right? So we can actually calculate this whole part, right? And we can calculate this bit, and we can actually calculate this whole thing at the end, but I'll leave that till later. So let's do some combining of values. Okay, so if you look at what happened here, right, our units kind of canceled. The moles squared are going to cancel with the moles and liters squared, and we're going to be left with atmospheres here. Over here, our liters, they stayed the same, so we are left with liters there in that thing, but the moles here, they're going to cancel out. And so all I did was I took these numbers on the left side of the equals and combined them. All right, so now if we look at what's going to happen next, our moles here are going to cancel there, our Kelvin's going to cancel here, and we're going to be left with a number that's in atmospheres liters. So let's calculate the right side now, and then we'll continue our calculation. All right, so this is what we end up with, and now we can divide both sides, right, by 33.786 liters, and those will cancel. And we have 33.786 liters, and the liters here will cancel, and we're going to be left with, all right, so we're almost done here. Now we just need to subtract over. As you can see, we're left with like pressure plus the 0.1908 atmospheres is equal to 21.38 atmospheres. Now we just need to subtract off the 0.1908 ATMs from both sides. And we'll get our pressure is equal to 21.19 atmospheres. And so here's our answer. This is the pressure of the container. And yeah, so there's a couple things that we should talk about before I finish this video, and that's that I, on a test, would never ask you for N or V, volume or moles, from this equation. on your homework, I'd feel totally comfortable asking one of those, but they are very difficult calculations. For instance, moles ends up being a third order polynomial that you have to solve, while volume I think is actually quadratic or something like that. So you got to be careful here. Um, Pressure and temperature are super safe. And so those would be the values I'd actually ask you to solve for on like a test environment. All right, if you have any questions at all, please feel free to let me know. And yeah.